This lecture is a review of a bit of geometry, and the reason that we're turning to geometry is that we're going to see soon enough that there's an important connection between geometry and probability when it comes to thinking about experiments. But for the time being, we start out with what's going to be the most important bit of geometry that's going to matter later on, and that's Pythagoras' theorem. So we've got a right triangle. It has a base of length A, it has a perpendicular side of length B, and it has a hypotenuse of length h, and you remember from your high school geometry that the square of the length of the hypotenuse is the sum of the square of the length of the base plus the square of the length of the other side. So here we have it, Pythagoras' theorem. The sum of the square of the hypotenuse is the sum of the squares of the other two sides for a right triangle. We're not going to really worry about it much, but this is one of many ways of proving Pythagoras' theorem, and it's sort of pretty. Very quickly, here's how it works. We've got a square with another square inside it, and that gives us these four similar triangles. The bigger square has a side of length a plus b, so the bigger square has an area of a plus b squared, and that can be written out this way. Another way to think about the same area, it's the area of the inner square plus the combined areas of these four triangles. What's the area of the inner square? It's just h squared. Each of the individual triangles has a base of length A, a height of length B, and it's a right triangle. So for each of these triangles, its area is a half AB. Add the four together, you get 2AB. So if this is equal to this, then when we take 2AB away from each of them, we're left with this, and that's Pythagoras' theorem. But the important thing here isn't the proof. The important thing is Pythagoras' theorem itself. We have the result that the square of the hypotenuse of a right triangle is the sum of the squares of the opposite two sides. With that in mind, we go on to something that you may or may not have known, but that's going to be important later on. Pythagoras' theorem doesn't just hold in 2 dimensions. We're going to see here how it holds in 3. So think of this as perhaps a rectangular sheet of paper on the table in front of you, and you're looking at it in perspective. So these corners don't look square, but they are. So the width of the piece of paper is B, the length is A, and here's the diagonal. And we know, of course, that the length of the diagonal of this rectangle is A squared plus B squared. That's just Pythagoras' theorem again. But we can extend it to 3 dimensions, and here's how it works. Here we have a line perpendicular to the plane of the table, sticking up towards the ceiling. It's of length C, and now we have a new right triangle. Okay, this new right triangle has a base of length H and a perpendicular side of length C. Its hypotenuse is capital H. Now, since this is just a right triangle, Pythagoras' theorem in 2 dimensions tells us that the square of big H is h squared plus c squared. But we already know that h squared is a squared plus b squared. So this line here has a squared length of a squared plus b squared plus c squared. Here's another way to think of it. Imagine that you have a rectangular box. Take a diagonal from the upper right corner of the box to the lower left corner, or any other diagonal that goes clear across the box. The squared length of that diagonal is the length of the box squared plus the width of the box squared plus the height of the box squared. Now, although we're not going to try and picture it, and we're not going to talk about it any further here, this goes up into higher dimensions as well. We have versions of Pythagoras' theorem in 4, 5, however many dimensions you like, and later on that's going to be important. but for the time being, we just mention it. So with Pythagoras' theorem in mind, go back to the two-dimensional case, and now let's just remind ourselves of a little bit of trigonometry. Here's a right triangle, base A, perpendicular side B, and we're going to label the hypotenuse R in this case. The reason will become obvious in a minute. This angle here is theta, okay? What's the cosine of theta? By definition, for a right triangle, the cosine is the length of the adjacent side divided by the length of the hypotenuse. So the cosine of theta is A divided by R. The sine of theta, that's the length of the opposite side, once again divided by the hypotenuse's length. So the sine of theta is B divided by R. And of course, we can get to here just by one step of algebra. Multiply each side by R. The sort of more intuitive point is that to get the length of A, we take the length of this hypotenuse, and we multiply it by the cosine of theta. To get the length of B, we take the length of the hypotenuse and multiply it by the sine of theta. So this little collection of equations here is essentially just a tight circle that goes with the definitions of these basic functions. Now what we're going to do is we're going to rotate this triangle 90 degrees clockwise. So we're going to put its tip down here, and we're going to put it inside a circle. So here it is, it's inside a circle, and also we're going to think of this length R, the hypotenuse of this triangle, as having a length of 1. And so now what I want to do is I want to ask you to think about the coordinates of this point here. The coordinates of the point where this line from the center to the circle, this line of length 1, meets the circle. Well, we know that if we go along here from the center up to this point, where we project down from here, we get a length of A. So the first coordinate is going to be A. We know that this length here is B, and so when we project it down here, the coordinate along the horizontal axis is going to be B. And we also know something else. Because of the way that the cosine and the sine are defined, you know that in each case you divide by R. But if R is 1, what that tells us is that A, the vertical coordinate of this point, just is the cosine of theta. B, the horizontal component here, the horizontal coordinate of this point, is just the sine of theta. And now that leads us to something else that's going to be particularly important. Okay? A squared plus B squared must be R squared. That's Pythagoras' theorem. But R is 1. And so A squared plus B squared, in other words, the cosine of theta squared plus the sine of theta squared must be 1. And that goes for any point along here. Pick any point you like on this circle. And if you take its coordinates, there's going to be an angle from this vertical to this point. Whatever that angle is, call it phi if you like. The coordinate of this point here is going to be cos phi and sine phi. And when we square the cos, square the sine, and add them together, they add to 1. So this little relationship here, a basic trigonometric relationship, is important. Why is it important? Well, just a bit of foreshadowing here. The reason it's going to matter is something like this. Suppose we're doing an experiment with just two possible outcomes. Maybe it's flipping a coin that might be biased in some way. Well, the two lines here could represent the two outcomes of the experiment. These experimental outcomes are going to have different probabilities. If we pick a point on the circumference of this circle in the right way, then the square of its first coordinate can give us the probability of one result, and the square of the second component can give us the probability of the other result, and those will add to 1. Now, this may not be very clear at the moment, but later on it'll turn out to be very important. For the time being, hold on to the trigonometric relationship, and also remember that because Pythagoras' theorem doesn't just hold in 2 dimensions, there's going to be an analog of this that'll hold in as many dimensions as we like. Okay, so here's what we've got. This is the little bit of geometry that we've reviewed, and this is what I want you to hang on to. First, Pythagoras' theorem. The square of the hypotenuse of a right triangle is the sum of the squares of the 2 opposite sides. Translate that into something about rectangles. The length of the diagonal of a rectangle is the sum of the squares of the width and the length. This also goes in higher dimensions. The length of the diagonal of a rectangular box is the sum of the squares of the width and the length and the height. And then, going back to 2 dimensions, we have this little trigonometric fact here, that for any angle theta, no matter what it is, the square of the cosine of theta plus the square of the sine of theta is 1. So this is a small handful of geometric facts. They're going to become important later on, but for the time being, review them again if you need to, but make sure you feel comfortable with them.